In this lecture, I will explain the scattering in nuclear physics. And this lecture is meant for people who have a very little knowledge of physics. So nuclear physics is important, in many aspects. For example, the first is the energy generation. With the help of the nuclei, we are able to generate energy. All right. So this is it can be for peaceful purposes, or it can be for uh, uncontrolled energy, which is atomic bombs or things like that. The other importance of nuclear physics lies in this nucleosynthesis, where we build elements, after the Big Bang. So we have a theories, and that theory explain how the elements are built up. The third is the batteries. There are lots of work on the batteries. There are a lot of work on nuclear batteries which work on radioactivity, and also there is a lot of work that is on uh, materials to get them heated up. For example, in outer space, we have objects that they are cooled down, so you want to heat them up. So nuclear energy is something which can be used to heat up those objects. And then the fourth is the understanding physics itself. So we try to understand, that what are the quantities that are conserved in a nuclear reaction. What are the importance, what is the conserved quantities in nuclear forces, all right? And also, we want to predict, for example, and explain the various scattering processes that take place. So these are some of the things, that are which are important, in nuclear physics, but we will be discussing only scattering. So let's go to the next slide. Now, explaining structure in nuclear scattering, and what is structure, we'll come to it in the next sections. We'll know what is meant by structure. In nuclear physics, or in other parts of physics also, and wherever you have this scattering, we normally use this what is called as the center of mass coordinate system. So the experiments are done in the laboratory, but these are converted into center of mass. And the reason why we use the center of mass system is that whenever there is a nuclear reaction, whenever you have a projectile hitting a target, so some of the energy is taken away and it is not utilized in the reaction. And that taken away energy is not apparent. It's already finished. When we work in center of mass system, that energy that which is not used, doesn't come up. In the laboratory system, if we try to put physics in the laboratory system, that extra energy comes up. But in the center of mass system, that extra energy which is not used in the reaction does not come up. So that is why we use the center of mass system. Now the center of mass is over here. It is on the heavier side. These are the two particles, and the center of mass always lies on the side where the heavier particle is there. So this is a heavier particle, it's the target, and this is the lighter particle, which is the projectile. And the center of mass, of course, lies between them. So let's see what happens when this projectile hits the target. So you see the center of mass moves also, and it lies between the two, not between, on the side of the heavier mass. Now in the center of mass system, you can have the same reaction taking place, but now the extra energy doesn't appear, and so only the energy that appears in the reaction appears. So see how the reaction in the center of mass system, the physics remain the same, but our platform of observation is the center of mass. That is, we move with the center of mass. So the center of mass remains stationary, and you see the scattering angles are different in both the systems. So you can convert from one system, that is a laboratory system, to the center of mass system, and you can also convert from the center of mass system to a laboratory system. The different energies, different angles, the different, and so on. So angles can be converted from one system to another system. Now over here, we consider a simple scattering process. You have a neutron, for example, and you have an alpha particle. This thing is extra. This shouldn't be over here. So let's see now what really happens. What we expect is scattering. The detector is over here, and this is the scattering angle. So the particle comes, it is scattered from here, it enters the detector, and this is the scattering angle in the laboratory. So this is happening in the lab. So you see that nothing spectacular happens, nothing special happens. But if you change the energy of the neutron, if you change the energy of the neutron at a specific energy, something different happens. Let's see what happens. So when you change the energy, what really happens is the neutron hitting the helium nucleus forms a molecule, a helium-5 atom for a very short time. You see. So you have helium-5, but this helium-5 is actually unstable. It's not stable. And it lives for a very short time because of this Planck's constant. This is Planck constant h divided by 2 pi. The value is very small number. So because of this smallness of the Planck constant, the helium-5 is unstable and it lives for a very short time. And you can calculate the time using doing an actual experiment. You can calculate the time during which the helium-5 survives. So you see, so this is the experiment done. The neutrons are coming there at different energies, and at one particular energy, which is near 1 MeV, you observe a lot many neutrons. So you see, this is the ratio of the neutron observed at large energy to the neutron observed at other low energies. So you see that at this particular energy, a large number of neutrons observed, and in fact, you have 10 times more neutrons being observed at this energy than at the high energy. And to get the time of the helium-5, you divide the Planck constant uh, up with this quantity gamma. The gamma is actually the width. We call this the width of the scattering width at this. So helium-5 stays for a very short time, and this was the main problem in the element building. In the element building, it was proposed that after the Big Bang, the neutron keeps on adding and the masses of the elements keeps on increasing. So this is how the elements were built up. This was one of the hypotheses, that was proposed by some scientists. But when it came to atomic number 5, say helium-5 with 5 particles, helium-5 lived for a very short time. Had helium-5 lived for a longer time, we would have got lithium-5, because if it had lived for a long time, then one of the neutrons would have decayed. We would have got lithium-5, and another neutron could have also added to it and also could have added to helium-5, and we would have got other elements also. So the building up of elements was challenged, because of the very small lifetime of helium-5. Now let's go to the next. Now before we move further, let's delve a little bit on energy conservation. A very simple way to explain it is through the pendulum, oscillating pendulum. We have plotted here, this is the y-axis, this is the x-axis, and over here y is 0. So the potential energy of this mass m is in the gravity is given by mgy. Y is 0, so the potential energy is 0. This mass is also at rest, so the kinetic energy is 0, so the total energy at this point is 0. So the total energy is 0, and total energy has to conserve. It is conserved, we know that. So as the pendulum swings, its y changes, its y decreases, so the potential energy decreases. Since the energy has to conserve, the decrease in potential energy is associated with an increase in kinetic energy. The result should be that adding the two should give you 0 energy. So if you see here, you have a very low potential energy, you have a very high kinetic energy, you add them and you'll get 0. So the swing of the pendulum is, for example, here it swings and you can see how it goes. So energy conservation is the cornerstone of physics, chemistry, biology, all sciences actually. And as you can see over here, this is a very simple potential energy. In the case of a nuclear forces, electrical forces, it's more complex than this. So let's now move to the nuclear forces. Let's see what the potential energy there is. So we consider first over here, we consider a neutron. This is a neutron, and this neutron is incident on a uranium-238 nuclei, and the center of the nuclei is over here. The potential energy between the two, between the uranium U-238 nucleus and the neutron, is given by this curve. As you can see, at large distances, it's 0. The potential energy is 0. All right. Over here is the potential energy in MeV. Over here is the distance in Fermi. 1 Fermi is 10 power minus 13 centimeters. So the neutron is sitting over here. It's not really sitting. We assume now that it moves with the kinetic energy of 5. So it moves with the kinetic energy of 5. So the total energy over here is 5, because the potential energy is 0, kinetic energy is 5, total energy is 5, and as it approaches the U-238 nucleus, the total energy of the system has to be 5. All right. And in order for that to be 5, as the neutron approaches, it has to increase its speed, because, for example, over here, at 1 Fermi over here, if you go over here, the total energy, potential energy is something like minus 43.5. So the kinetic energy at this point has to be plus 48.5, if we want the total energy to be plus 5 MeV. Hence it speeds up, and you can see from this footage over this graph over here, it speeds up over here. And of course, many things happens actually over here. When the neutron can hit the uranium U-238, it can get absorbed in it. And after absorption, the uranium U-238 can get converted to, plutonium-239 after some reactions. Or a neutron can simply be scattered off the uranium-238 nucleus. Another thing that can happen is the neutron can hit the uranium-238 nucleus, and it can cause the uranium-238 nucleus to split into two parts. and that is, we know that we call it fission. And another thing that can happen is, for example, the neutron after hitting the uranium-238 can cause the uranium-238 to undergo oscillations. And in this way, you have inelastic scattering. So there are many things that can happen, of course. The whole idea of this slide was to tell you about the potential energy curve. You see that at large distances it is zero. There are no peaks over here. The energy is only negative. Potential energy is only negative or zero. Why? Because there are no repulsion between the neutron and the uranium-238. Next slide shows you. Now this is an experiment between the charged particles, oxygen and oxygen. Oxygen has 8 protons each. So there you have a scattering taking place, and over here you have the number of oxygen atoms, nuclei that are scattered. And over here you have the incoming energy, the total energy of the system, all right? And you can see that you have two types of peaks over here, you know. One type of peak are the broad peaks. You see the broad, they are very broad. And the other type of peaks, they are very narrow peaks, all right? The broad peaks are called gross resonances, and the narrow peaks are called intermediate structure. Now the gross peaks, which are they are explained very simply, but the intermediate structure, all right, is difficult. The gross structure is simply explained, The dash curve over here, explains very well. For example, over here it explains very well. The experimental gross structure, the dots are the experimental points, and the dash curve over here is the theoretical curve. So the theoretical curve explains very well the gross structure, as you can see. The intermediate structure is the one that is very difficult. So let's go to the next slide and see how let's see how these things are explained. So you have the two oxygen nuclei over here, and this is the target, this is the projectile, and this is the potential energy curve. All right, now this is of course much different, very, very much different than the curve we had of the pendulum, because there the curve was due to the force of gravity. Here, this curve is due to the nuclear forces and the electrical forces of the two oxygen nuclei. And this curve was actually presented first by Werner Scheid and Walter Greiner in their famous paper. And over here, as you can see, there is a peak over here, and this is called Coulomb barrier. When the particles, these two, are separated from far apart, they are more far than this distance, which is 7.85 Fermi. So when the two particles are at a distance greater than 7.85 Fermi, the only force is the electrical force, and you get this curve, all right, this curve over here. Q1 and Q2 are the charges of these two, and R is the distance between them. Anybody familiar with elementary physics knows that this is the potential energy of the two charges, Q1 and Q2, separated by a distance R. So over here, only the electrical force is operating, and when the two nuclei come closer together, closer than this distance, the nuclear forces start to operate, and then you have the strong nuclear forces which make this curve go down. So the curve is going down, it goes down. And this is where you have the attraction between the two nuclei. So the repulsion is here, the attraction is here. And of course, when these nuclei try to penetrate each other, which is very difficult, So you have this repulsion again. Because when they penetrate, there's a lot of compressive forces, and these forces don't let the two nuclei penetrate each other. So the curve that you saw over there is we have the experimental curve. We have plotted over here, in a very simple way, easy to understand. And again, you have this gross structure. And then you have this intermediate structure. The gross structure, for example, is around 2 MeV wide. You can see over here, it's around. And the intermediate structure is around 0.5 MeV. So what does that mean? This is, remember, the gamma we discussed last time. So the gamma comes in the denominator. So whenever you have this gross structure, it means the nuclei, the two oxygen nuclei, when they come together, they form a sort of a small complex, but for a very, very short time. But over here, when at this energy, for example, they would form a complex which would live for a large amount of time, because the width gamma is very small, is only around 0.5 MeV. So now to explain the intermediate structure is very difficult. To explain the gross structure is very simple. You see, it is explained over here using the real potential that I showed in the previous slide. Plus, we also have to include to it an imaginary potential, which is a potential that is responsible for not only the scattering but also the other reactions that take place. All right, so when the oxygen hits the oxygen, there are other reactions that can take place. For example, one of the oxygen atom can break up into an alpha particle, and a carbon nucleus and an alpha particle. So many reactions can take place. So in order to account for those other reactions, lump sum, we include another potential which is called imaginary potential, which we are not showing over here. So the theory and experiment are close together right up to this energy, because our model actually is only for high energy. That potential you saw was for high energy, so it works up to this energy. Now let's see how we can explain the intermediate structure, okay? So let's go further. Now over here, we have got this intermediate structure produced from theory. You see, this is produced over here. And how it is produced? It is produced by assuming that one of the nuclei, starts to oscillate. Because when it oscillates, if one of the nuclei oscillates, for example, if this oscillates, some of the energy which was the motion energy, the energy of motion, goes into oscillations. So how much energy goes into oscillation? 6.9. 6.9 MeV of energy goes into oscillations. And so if you see this potential energy curve, so now instead of the 20.3 MeV, you see 20.3 is over here. This is where you are getting this intermediate structure. So at this energy, which is 20.3 MeV, one of the oxygen atom comes at 20.3 MeV. The total energy you have 23.3 MeV at the total system energy. So at 20.3 MeV, one of the nuclei starts oscillating, and the total energy of the system still again is 20.3 MeV, but it's now divided into two parts. One is the oscillating energy, which is 6.9 MeV, and the other is the energy of motion, which is 13.4 MeV. So, and now see what happened. Let's see the oscillations taking place, and you see one of the nuclei is oscillating. This is oscillating, and so one of the nuclei is oscillating, and you get to this energy. And sometimes you can also assume if both oscillates, you go down to very low energy, but This is very, very difficult because you can see over here, the centers of the two nuclei should be very near 6 MeV, and probably that is very difficult. It's very difficult that two nuclei can really penetrate that much. Now let's go to the next slide. So elastic scattering and inelastic scattering, instead of vibration, you can also have rotation. Now in nuclear physics, a spherical nuclei cannot rotate, all right? It has to have some deformation. So over here, I'm showing a deformed nuclei. This is a deformed nuclei. It comes over here, all right, and it forms this molecule, all right. And when it forms the molecule, you see you have elastic scattering, and then you can also have inelastic scattering. Let's see how it works. So over here, you see you are having this molecules form for a short time, and one of them is rotating, and then they goes up. You have elastic scattering. And the other thing can be inelastic scattering, where again you have these two nuclei rotating. One of them actually rotating, one of them is rotating, the other is just going around, and there, this is inelastic scattering because the energy of motion is taken away by one of the nuclei over here, and it is rotating. So this is inelastic scattering. Now I hope that you have understood my lecture, at least the layman. The idea here is actually to tell you what goes on in nuclear physics, and people who are interested in it should know, this whole actually approach is done actually through the quantum mechanics. The real scattering is done through quantum mechanics, where the incident projectile is represented by waves. That the waves and the target is actually simply a potential energy curve. So you have a potential energy curve on which waves are incident, and those waves actually go inside, and then they can be scattered, they come out, they come back. So all this is actually quantum mechanics. It's the physics of waves, but special type of waves, which we really call matter waves, waves associated with matter. Every one of us have that wave. Me, you and I, the earth, every one of us has a wave. But when these waves become very small, like the wave that we have, like the wave that is in a football, like the wave, in a golf ball, or a wave associated with anything like a car, it is very, very small. So you can apply ordinary mechanics. You don't no need to apply quantum physics. So quantum physics is basically applicable at very small level and not at the basic level where ordinary mechanics is okay. All right, please keep seeing my channels, and I hope this would give you some understanding.